हेलो। 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 थैंक यू।
ഹോസ്പിറ്റലിലൊക്കെ ഇരുന്നുണ്ടായിരുന്നു. అది FTP అంటారు.
FDP-నా? ఇంకెంత సర్టిఫికెట్లు కావాలి? ఎంత డెవలప్ అవుతారు మేడం ఇంకా?
Good morning, everyone. Welcome to our third day of hybrid mode faculty development program in recent advancement in material science and medicinal chemistry. We are fortunate to have with us today's speaker, Dr. Y. Saujanya Ma'am, Senior Principal Scientist, CSIR, IICT, Hyderabad. We are honored to have such a distinguished group of faculties and researchers joining us. Before starting the program, I would like to invite Professor Savita Belwal, ma'am, HOD, Department of Chemistry. Ma'am, please grace the stage. Now, please give a warm welcome to our today's speaker, Dr. Y. Saujanya, ma'am, as she joins us on stage. Ma'am, please. Now, I would like to invite ma'am, Professor Savita Belwal, ma'am, to present a sapling to Saujanya, ma'am. I hope today's event promises an engaging and enlightening experience for all of us. So let's begin this journey of learning together. Thank you for being here. Before starting this program, I'm honored to introduce to all of you with Dr. Saujanya Ma'am, Senior Principal Scientist from CSIR, IICT, Hyderabad. Ma'am received her doctoral degree from University of Hyderabad. She has postdoctoral in France and Canada. Her research area of interest include computational chemistry, CO2 capture, and utilization for value-added chemicals. She has more than 25 years of research experience in computational study of materials for various applications. She received Dr. K.S. Krishnan Research Award and Research Associate Fellowship from CNRS France. She published more than 80 research publications and a book chapter in various conferences and peer-reviewed international journals with more than 2,000 citations and 29 H-index. As of now, she has supervised 5 PhD research scholars. Now, I would like to invite Professor Dr. Saujanya Ma'am to share her valuable insights, please. Ma'am, please.
It should be audible for.
Yeah.
Yeah, it works.
I think I can be loud. Or you need this mic?
Yes, madam. Speakers unnara online.
Okay.
Reverse fit.
One minute.
Can I have?
Yeah. This is for.
Yeah.
This one.
This is pointer. This is no. Okay.
Almost 30 to 45 minutes.
Different.
Okay. Fine. Yeah. Yeah. You'll have some discussion and then we can. Yeah. Yes. Very good morning to all of you. Yeah, I see a lot of students here. You are all PG students or under? I should be careful because uh, you are PG students or pharmacy, final year pharmacy, and okay. Are there no students from chemistry? Yeah. Okay. Yeah. No, no. I really enjoy talking to students more than anyone. So I'm just inquiring about it. So thank you for giving this opportunity. This is a kind of refresher. Our though we do every day in our institute, talking the basics fundamentals is a kind of refreshing course for us. Thanks for inviting, madam, Dr. Suman. Yeah, thank you very much, and thank you, faculty, all the faculty here. So since I'm just changing my discussion is a kind of discussion, you can interrupt me in between so that you can clarify then and there itself. It is not a very formal presentation. Um, it is basically I'm trying to give you the background of computational methods. Like and many of you have used several software, right? Can you name any software which you have used for your computational work? Sorry, Flexicom for Flexicom for which application you have used it? For drugs, like you, is a structure based ligand design or docking or? Okay, 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 good. But uh, it is highly important to know the basics, the fundamentals of methods that are there. You can just buy a software or you can download any software from open source, or you can buy it and then you can run it for your molecule or anything. It is garbage in, garbage out. What I say, you submit anything, you ask anything, it will give some number. But what number it gives, will it make any sense for us to understand the numbers or results it will give? So this is the institute from where I'm coming. As you know, this is out of 37 labs that got spread across the India. We were in Hyderabad, so you know CCMB, right? CCMB, NGRI, they are all come under CSIR. So basically, we are almost touching 80 years of service to the nation. It is different from other institutions like IITs, NICERs, or NIPER, in the sense we are more focused uh, to address the challenges of the industry rather than the pure academic. Academic, we have a PhD program, but basically we are into giving the services to the industry or addressing the problems of the industry or society that is currently facing. So, and as I said, it is, you take any software, you submit anything, you ask the computer anything, it will give some numbers. The real challenge is how to interpret the number, because if you don't know the basics, it is driving the car without license. You will get something, you get some answer, you can interpret, but unless you have that fundamentals, the basic, the background, what is going on in the software, then only you can have a real picture of the problem. So this is the jargon of nomenclature because there are several terminology is given. You can be a molecular modeling because you deal with a small molecule, small amino acids, or small transition metals or elements. So in that sense, it is called molecular modeling. Computational chemistry, you are all aware what is the computational chemistry, theoretical chemistry is different from computational chemistry, because in computational chemistry you don't write the programs, you don't develop a software, you just use the already available on web, or you open source and use it. In theoretical chemistry, like you literally work on the atom or molecule and then try to write the programs. Okay, so then it is called theoretical chemistry. Simulations is one kind of term. And quantum chemistry, that is the basics, whether it is a pharmacy or chemistry or anything, chemical engineering, the quantum chemistry, or which is the basics called quantum mechanics, that is the backbone which you have to understand, which you should know the fundamentals. And computational bio, if it if any problem deals with the biological problems, it is computational biology. If it is a chemistry related problem, it is called computational chemistry. And as you know that in doing this kind of calculation, either you have a standalone system, like you just take one amino acid or one material, or like graphene or any nanotube. So this is a standalone system. You try to understand what are its properties and all. So that is called a static calculation. But if you want to do how it behaves over the time, like it is called time dependent molecular dynamics. So that is actually very expensive than the standalone calculation. So there are again there are several programs or software available to do only the molecular dynamics. Can you just give me any time frame usually which molecular dynamics will be carried out? For which, for how much of time duration usually the dynamics will be carried out for any protein or any uh, uh, nanoseconds? Perfect. It is even nanosecond is a very expensive. So it may go to picoseconds, femtosecond. Like if there is any protein, how it folds over the time. Okay. So this kind of calculations is very expensive. And so what is what is that we are looking for? What is that we are going to get from these calculations, from these methods? So you have the molecules, you have the system, any problem in front of you. You want to know the properties, how the conformation of a molecule will look like, what are the energies of it, whether it is a very high polar molecule or a non-polar molecule, whether this molecule will get solubilized in any solvent. If you take any solvent like water, dimethyl ether or anything, can we predict a solvation of a particular molecule? So these are n number of properties that we are looking for. So exploring the structure property relationships. Structure property relationships means you have one kind of a molecule, and depending upon its conformation, you have one property. If you change this conformation, or if you change any kind of functional group, it will have a different property. So you build up a data of all these different structures, and you get the property, and then you can relate. That is called the structure property relationship. And the reactivity of the molecules, as you know in organic chemistry, how a chemical reaction will take place, what is the operating conditions, temperature, pressure, whether the reaction will go in forward or backward. So what are the probability of getting the product? So impurity presence, all these things can be done using these methods. And supramolecular interactions, you know, in DNA molecule you have a non-bonded interaction, right? Why it is called helix? Because helix is formed due to non-covalent interaction, which keeps it in a helical mode. So these non-bonded interaction we can calculate using this methods. So there is a, have you heard of Richard Feynman? He's a very, basically he's an eminent physicist who is the father of computational chemistry or quantum mechanics in other way. So there is a plenty of room at the bottom. So this is just what I said. Energies, structures of optimized. What do you mean by optimized? You take one, can you give any example of amino acid? Histidine, right? Histidine is a 5-membered ring. It has 2 nitrogens and 3 or 4 carbons, right? So you start, you don't know how the molecule will look like. What is the the practical way of looking the molecule? You don't know. You want to ask the computer what is its structure. So you randomly start with some, you draw a structure of 5-membered ring and keep 2 nitrogens and then see carboxylic acid, and you ask the computer, okay, you try to give the lowest energy possible. So like if you, in another group of institutions, if what is the optimized way of finding maximum number of students at a given point, at which point you can find in a canteen or any other location where you can find, where there is a lot of attraction, right? So something like that, like you have a probability of finding a very definite and energy wise it is the lowest possible structure. Then you are asking the computer, you find that lowest possible and you find that the minimum structure, minimum energy structure, that is called the optimization. So it is in the background, there are several equations. This is called self-consisting field iterations. So you have started pentagon in a very random fashion. You gave what is CC bond distance in a pentagon? For example, in histidine, C double bond C distance. No answer. 1.2, 1.3. So you start with 1.4. Okay. So you ask the computer, okay, it has to be have conjugation, it has to have a lone pair effect and all. And then computer will do a series of iterative equations in the background, and it will bring down from the highest possible energy, what you have started, to the minimum, the lowest possible energy. That is called the optimization. So there are several methods to do this procedure, which I will tell you in coming slides. So energy structures of the optimal, once you reach the lowest possible energy, that is the practical way of, that is the final geometry. Then you can take all its electronic properties like bond length, bond angle, twist angle, dipole moments, charges. So all these properties, you can say that, okay, this molecule will have this kind of properties it will have. You can check with the experiments. How close it is to the experimental values depends upon the what kind of method you are using. So as I said, it is garbage in, garbage out. So you get what you ask the computer, it will give some number or some results. But how to validate it? If can you just tell me? You ask the computer to find out the structure or any conformer. So how do you validate that given structure? Is it correct or not? How do you do that? How do you do that? Any guess? Fulfill. If you have any experimental data, for example, if the crystal structure of histidine is available in the public domain, You just compare whether the structure of that molecule, whatever method you have used, whether it is close to the experiment or not. If it is not close to the experiment, then your method is not good. You have to go again and then do it again. This is called validation. So that is very important. How do you do that? Only when you get the fundamentals of the quantum chemistry, quantum mechanics. So how to choose the methods? I will give you very important outline here. For example, you have histidine, right? Histidine, 2 nitrogens and carbon. Carbon, what is the electronic configuration? Valence shell. 2s2, 2p2. So it has four valence electrons. So, and it will have nucleus. And nucleus will have, it has protons and other neutrons and other things. So, for just a given atom like carbon, you need to have a very good starting point where it can predict the position and the mobility of a given electron with respect to the nucleus. Okay. So, for example, you have a carbon and these electrons are rotating around the nucleus. These electrons will have a electron-electron repulsion, right? And it will have a electron nucleus attraction. There are several forces which actually it is working for a given atom so that it will be bind together to have a histidine molecule, right? So how do you take into consideration while doing the methods? So how do a computer will take all these aspects into consideration in doing the calculation? So let us start with a single atom. Single atom like hydrogen, carbon, nitrogen, or any kind of atom. So it will take the penultimate electrons of each atom, and it will take the electron-electron correlation and other interactions into consideration, and it will try to optimize the elemental composition. So then these atoms will bind together to form a molecules, and these molecules will have non-bonded interaction, or it can aggregate to form a macromolecules. So how do we choose any method to predict the properties? Either a single atom, we can do the calculation either for a single atom or for a molecule or for a macromolecule. So if you want to hydrogen, right? Hydrogen is well known, right? Hydrogen is a green fuel compared to fossil based fuel. So how the hydrogen will behave? What are its properties? That is based on atom based calculation. For example, if you go for a molecule, it is a molecule based, and then which will aggregate to form a macromolecule. So choosing a method depend upon the size of your problem, whether it is a single atom or a molecule or the macromolecule. So there are several hierarchy of methods, like you have a very expensive method which will take all the calculations, all the properties of these atoms or molecules. That will be very expensive. So you need to have an approximations. So these are the methods that are available, and we have to choose these methods based on the size of the size of the molecule. So that is why I am giving this slide. So these are the methods that are available. Is ab initio method. Have you heard of Schrodinger equation? Schrodinger equation is an Austrian based physicist who has developed the Schrodinger equation, that is the backbone for the quantum mechanics. So can you anyone give the basic equation for the Schrodinger equation? Exactly. H psi is equal to E psi. That is the psi is the wave function. Wave function is the major, is the important improper parameter which will give the which will work for our problem. So this is the ab initio methods, and you know the classical mechanics. So Schrodinger equation is for the quantumized energy levels, is for the molecules. For example, if you go for any spacecraft, so how the Earth rotation will be, how any rocket will have a kind of its rotation around the moon or something like that. So if you want to do simulation for such kind of problems, it should be based on classical mechanics. For molecule, for atoms, for any kind of supramolecules, the method should be based on the quantum mechanics. The background for the quantum, important backbone of the quantum mechanics, the Schrodinger equation, and that is called ab initio method. And you know, sir, can you do ab initio method for any big protein? You know, there are several atoms in protein, right? Any guess how many atoms will be there in a given protein? How many atoms will be there in a given, in any protein, approximately? Some 100, 200, right? Because it is a threefold folding protein, right? It will have several atoms and several interactions. Can we use very expensive technique? What I said, it's based on Schrodinger equation. Can we use such methods for protein? It is, in our lifetime, it is impossible. So we should have some approximation, and that is called the semi-empirical method. Semi-empirical method means it will take the values that is already there in the databases, that is experimental data. So for example, if you find any CC bond in any protein, if there is any CC single bond, it should not calculate. There is no need to calculate for a computer. It will blindly take the CC bond length 1.5. C double bond C, it will take the C double bond C. So it will not calculate the important parameters that are already known, established. It will take the from experimental values and then give the results. So automatically the time will be reduced compared to the ab initio method. So this is the semi-empirical method, and the molecular mechanics is based on the semi-empirical method only, but it will not use the Schrodinger equation. So, for example, you want to have very accurate method. You want to get the perfect, very close to experimental value, very correct value for any protein. How a given protein will solubilize in water. Okay, so that is the problem you have. But you don't want to compromise. You still want to have very good method in you don't want to have very deviated number. Okay, so what you do is you define a box of a protein in a water, and you know the active site, right? Active site is very familiar for all of you, right? Active site is where the ligand will bind. So you take the active site, a critical region of the protein, you use the most expensive computational method only to this region. And the surrounding region, you use the very approximate method. In that way, you are balancing both the accuracy and the computational time. So that is called the QM-MM. You are using QM for critical portion of your protein, and MM, which is the approximate method for the whole box. So this is just repeat of what the Schrodinger equation is and the molecular mechanics. So you know that electrons are in a constant motion around the nucleus. And in developing these computational methods, there are several approximations because it is impossible for any scientist to have any program or any software taking all the properties of these atoms. Okay, so in that way they have developed several approximations so that we can get the results at a reasonably fast methods, faster time. So this is Born Oppenheimer approximation. Anyone knows about Born Oppenheimer approximation? Anyone heard of Born Oppenheimer? Oppenheimer is the one, right? You recently watched a movie in the Netflix. He is the father of Manhattan Project, right? Oppenheimer approximation, right? In a given period of time, the nucleus will be fixed and only the electron motion is considered. So like that, there are very several approximations like Harvey-Fock, ab initio method, density functional methods, semi-empirical method. I said earlier, so we have to choose a method depending upon the size of our problem, size of our molecule. How many atoms are there? Are there any heavy metals in the elements in our protein or in any of your other problem, like heavy elements like iodine, bromine. So if you have a carbon, nitrogen, oxygen, these are okay. If you have any transition element like iron, cobalt, it will have d electrons, right? So depending upon the size, how many atoms you have and how the molecule will look like, you have to choose the method. So it's like if I want to go from Hyderabad to New York, I cannot take a bullock cart, right? I should have a kind of faster mode, but also at a cheaper price. So I take a economy class air flight or anything. Or if I still have a time, I can take a sea route, right? So like that, depending upon the nature of our problem, there are several series of methods. There will be n number of methods. It will be a kind of ocean for you. So then you have to choose from these methods which is more useful and relevant for your problem. So as I said, semi-empirical method, empirical methods, these are all the approximations which will give us some kind of outline for our computational methods. So coming to the important slide. So you have a to have a design molecule. So either you can have an experimental procedures for a synthesis, measure structure, measure stability from spectroscopical data, and this is the main factual data. So suppose if you don't have the experimental data, then you have to depend on the computational methods, which will predict the property of a given molecule. So this is so if you have it, you can compare with it, or if you don't have, you can suggest the synthetic people how a computational chemist will work. He will design a molecule or he can predict a molecule, and he will say the synthetic people, okay, you work on this molecule, it will be very useful. In IICT, we work, though we are a pure computational, we don't have wet lab, we don't have benches. We just work on the silicon graphics. We work on the computational methods. So how it will work for us? Suppose one of our Raj Reddy has come yesterday, right? He had a problem in his reaction. He has used two different type of catalyst. One is ruthenium and one is rhodium. And somehow he is not able to understand the difference in the selectivity of the reaction, because though both catalysts work in a similar way, if you use the ruthenium, you get one product. If you use the rhodium based catalyst, you are getting another product. He is unable to understand what are the driving force to get a different products using the same similar type of catalyst and also the reaction condition. Then he approached us. So what we have done, we have taken all is the information. What is the reaction? What are the molecule structure? So suppose he has taken, I think, some thiol compound. Okay, he has given the structure of the molecule and he has given the reaction condition, some 80 degrees in DMF solvent and so he has given some set of parameters. Then we have done in our computer, we have generated the structure and then we have chosen a method because it has I think ruthenium and rhodium are transition metals, right? It is very heavy metals. We can't use a very expensive method. So we use approximate method and then we have explained the reason. We have explained the reason why he is getting two different products for a similar catalyst. So that is the beauty of the computational chemistry. In absence of any experimental data, in absence of any other data, you can give the experimental people, you can provide the guidelines whether this will happen or this will not happen. Okay. So that is the beauty of the computational chemistry. So as I said, it depends upon the size of the molecule, size of your problem, whether it is a single atom or it's just only one hydrogen or two hydrogen or it is a H2O molecule. H2O has three atoms, right? H2 oxygen. So like that, if you vary the size of the size of your problem, your method also will change. So here like this, quantum mechanics, it is within 1 nanometers. Like if you have it may go to 2 to 3 angstroms for any water molecule or nitrogen and ammonia or any kind of such smaller molecules. Then if you go up to 10 nanometers, it is molecular dynamics you can do using mesoscale dynamics, and these are all the advanced methods to if you increase the size of your molecule. So similarly, this is for a general materials which I wanted to give you the time scale, and this is since we have many students from pharmacy, I thought how it will be useful for a given molecule like quantum mechanics for this kind of structure and dynamics for this kind of protein folding. So like that, the time scale will change depending upon the nature of your problem. Okay, so I mentioned earlier about the DNA helical structure. What is the driving force? Any student can tell me what is the major reason for a DNA molecule to have a helical structure? Hydrogen bonding. Hydrogen bonding and many other non-bonded interaction, cation pi interaction, pi interaction, n-pi interaction. So these non-bonded interaction are responsible for the helical structure. Similarly, water. Why water will have a liquid form? Because it has a hydrogen bonding. So we have to, using this computational method, we can even to the highest decibel point, you can very accurately predict the nature and the strength of these non-bonded interactions. So here, as I said, it is hydrogen bonding for a water molecule. This is metal ion lone pair interaction, anion pi interaction, CH pi interaction, and pi interactions. These are all kinds of non-covalent interactions, which any pharmacy or biology or chemist will always look into this kind of interactions. So how these non-call interactions will play in different areas. So it can have a self-assembly. So where it can stack one over other. It will have its role in catalysis, biology, and the aggregation. So as I said, water, it forms hydrogen bonded clusters. That is the major responsible for its nature, for its state. And you can have a different nature of clusters for this molecule and then calculate its properties. These hydrogen bonding, can you guess the strength of these hydrogen bonding interaction? How strong they are? You have a covalent bond, right? You have a covalent bond and you have a coordinate covalent bond, and you have a hydrogen bond. A hydrogen bond is stronger than covalent bond, or it's a weaker. It goes up to few calories to 10 calories. So, but if you uh, if all these kind of non-bonded interaction, if it works together, it is more stronger than any coordinate bond or any covalent bond. So that is called the coherent covalent bonding interaction. So here, all these non-bonded interaction work together, and though if you have such kind of coherence interaction, it can like what I have represented here as a two ants, it can either it can lift the it can lift the apple, which is actually much weight, has much weight than its ants, right? So that is where I'm trying to make you to understand that even they are weak, they work together coherently to drive the reaction. So that is what I wanted to tell you. So this is another way of showing you that how these non-bond interaction work in a cooperative way to drive the reaction or drive here I am showing in a kind of wheel. So tools like these are the major software which we are using in ICT. Gaussian, you all are aware of Gaussian software, right? Gaussian software, you are all aware. Gaussian is the major, uh, not very expensive. Does this institute has the license for the Gaussian? I think you can buy it. It's a one-time purchase, and you can have for whole life. And it will be very useful for the students how to draw a molecule, how to predict the structure, and there are so many workshops available online to use the software. I think maybe your HOD should recommend for the purchase of. Good. Huh? No, it can be for 10 lakhs. I'm not sure. Okay, okay. Okay, so we have Schrodinger, you all know, which is majorly used for. Now we have a Schrodinger for biology, and also we have a Schrodinger for material science. And all these
Oh, shit.
genomics and all, which actually we don't use, and other group members. Jaguar is for metals, transition metal based chemistry. So, and these are mostly these are for the open source. You can download these tools freely from online and then use for your problem. Okay, this is with this I just completed with just a um, outline of this computational method. Which method we have to take and how to take, and what are the properties we usually get it. I'm done with the time, or I have few. You have time. Okay. In our group, what we actually doing is for material science. So what we do is, we all know that there is a global warming and climate change, right? That is because of CO2 emissions into the atmosphere. We have a automobile industry, we have a cement industry, and the fossil fuels, right? Like IOCL, Reliance Industries, they take the oil from the ground and they give us what you fill in your automobiles from the any gas station, it is a fossil fuel, it's a natural gas, right? So if when you drive a car that will use that gas, in that process it is emitting the carbon dioxide into the atmosphere. So that is one mode of releasing gas into the atmosphere. Like that, every industry, like cement industry, steel industry, especially the coal industry, coal, the black coal. If you, to get the energy, we are burning the coal, right? If you burn the coal, 80% of the gases coming out is the CO2 gas. Because of that, we are facing several climate change problems because the emissions are increasing so high. Before industrial era, it used to be around 200 parts per million of carbon dioxide in the atmosphere. You know, now today it is reaching 453 parts per million of carbon dioxide in the atmosphere. So that has adverse effects both on our lifestyle and the climate and also our health. So here what is our major challenge for it is, how can we, because I cannot go back to the bullock cart. I cannot stop using automobiles. I cannot stop using cement. I cannot stop using steel or anything, right? I should have these things, but at the same time I should I can stop releasing these poisonous gases to the atmosphere. How a scientist can help? Here, we have developed a methods, we have developed a materials that can capture CO2 from the atmosphere, or it can capture you go to you have if you go by any train or bus towards Ramagundam or anything, you can see huge chimneys, right? Chimneys, and you will get gases out of the chimney, right? Even in any industrial area, in Nacharam industrial area, the flue gases are coming out of the chimneys. So those are all poisonous gases. So what we do is we collect those flue gases, the exhaust gases, and we pass through some kind of columns, absorption columns, where it will take away, it will absorb. Like if there is any water, if you use the sponge, it will take away the water, right? So like that, if flue gases will be passed through a column, and the column is filled with kind of material which we have developed in our lab, and it will selectively take out these poisonous gases and release the pure gases to the atmosphere. That is the major projects that is currently going on in our lab. This is very much useful for the industry. So another important area where I wanted to touch upon is, there are three important keywords, whether you work for a biology or chemistry or chemical engineering or anything. What is the major buzzword we are hearing now? It is relevant to any branch of science or any branch of can you yeah, exactly, it is artificial intelligence and machine learning. So you cannot escape from these methods. So in our what in the beginning I have shown a team, right? We don't work alone. I don't know, I do not work just for myself. We always work with the team member. My expertise in developing a computational method and trying to predict the properties of a given structure and generate the data. And another team member will use this data to develop the AI model or they will use my data to train the model and then develop the AI model and then predict the properties. And in that way, you can also design the new structures. So, and another one is the database. Database is, many of you know about it, right? So these are the three words: quantum mechanics, artificial intelligence, and machine learning. We work together to work in this direction. So here I said that these exhaust gases will pass through a column which is filled with some material. What is that material? It is a catalyst material. Because if you, a sponge means if you use that sponge, it will take away the water and you squeeze the water and reuse it, right? In a similar way, the material should take away and then we will take out the poisonous gases from it and then we reuse it, recycle it. So in that way, we don't need to use the new material for every time. So recycling is very important. So here I mentioned it is a catalyst material which will be filled in the absorption column. So what does this catalyst will do? It will try to, so in these flue gases, the major one is the carbon dioxide, methane. What is the dipole moment of carbon dioxide? Anyone knows? 0, because it has no active, oh no, yeah. So it is very stubborn molecule and it is very unreactive. To make it to my material, if I want that one to bind to the CO2, it should have a lot of properties, right? Because it is very stubborn molecule. It will not get attracted. So here we have designed in a such a way that it will try to attract, make the structure to bend. It is a linear molecule. It will bend in a such a way that it will try to attract to the material. In that way, we can take out the carbon dioxide. Like that, apart from carbon dioxide, we also have the methane. Methane is also a highly inert molecule, CH4, right? And CH bond is highly strong bond. So have you heard of CH bond activation? So CH bond activation is also very important in it has several applications. So we design our material to activate this CO2 and also activate the CH bond in a methane so that it can form the bind with our materials and then we can take away the poisonous gases. So here what we do how do we use the artificial intelligence and machine learning in our work area? So as I said, I generate the data using Gaussian software or Quantum Espresso or VASP is another software. So we use different software to generate how this catalyst molecule will behave. So these catalyst molecules are basically based on transition metals. So we generate the data and that is called data collection. So we use our catalyst material will have an active metal and it has support and the promoter which will which will bind to CO2 and methane molecule from the exhaust gases. And then we collect the data for the operating conditions. And then we give our data to our team member who will use the model development using AI/ML tools. From that model, he can inversely design. Okay. So for example, you have a classroom of 50 students. So if I take a data of each and every student, like height, weight, eyeball color, hair color, or whatever the properties of the whole students of a class, I generate the data. Okay. So in this data, in this classroom, majorly I have these parameters, which you can make a model. Okay. So 30 girl students and 20 boy students. So 30 and 20, 50. Okay, 50 students will have these parameters. Then I can use this data to have an inverse design. I can predict in any other classroom, this many people, this many students will have this many properties. That is called the inverse design. So using our data, our team in AI/ML, they do the inverse design to come up with a new material, which will have more effective than what we do in our lab. And finally, we do validation. That is very important. Whatever we do in using any computational method, no one will believe, right? Okay, I cannot say that, okay, my molecule will, I have designed this molecule using very expensive method. This is very accurate. I can boast any kind with any kind of force and I can force anyone. But what is the validation? Unless I use it in an experiment, unless I go to an industry, we don't go to industry because in our lab we too have a pilot scale equipment, right? So unless we do the experimental validation, no one will listen to us. So we do the experimental validation, and then the success of it will depend how effective and uh, how important that material is in catalyst design. So this is a summary of it, which we use. We either generate the data, use the database from any open source, or we use the computational methods, ab initio method, Schrodinger equation, which will generate the data. The data majorly used for how the reactant will form the product through transition state, and these are all the properties. Descriptors are nothing but the properties of a molecule. So these are all the properties which we generate, and our team members use the AML tools to develop a model and then design a novel catalyst. So as I mentioned before, it is the CO2 capture from the exhaust gases of the industrial exhaust gases. That is a major challenge for us, which we use our materials to selective capture of CO2, and also for conversion of these greenhouse gases, that is methane and carbon dioxide, to any value useful chemicals. So this is another kind of summary which I wanted to. So here, this is the major outline, whatever I have explained till now. So how many types of methods, and how we have to choose a given method, and how it depends upon our problem. So we have a quantum mechanic method, which is again semi-empirical. I mentioned semi-empirical method, right? And density functional theory, it is one kind of approximate method which is dependent on the charge, which is developed based on the charge of a density of a atom. So that is called density functional theory, ab initio method, molecular mechanics, force field. I'll just give a small, very simple question to, if anyone can understood what I have told till now. Which method you use for protein? Of all these methods, which, huh? Semi-empirical method. Semi-empirical method also is a kind of expensive. Molecular mechanics. Molecular mechanics is a very appropriate method to use for your molecules like proteins. Okay, this is so I said, like, we have designed a catalyst molecule, right? So this is a overall like it is a nickel cluster. So how the nickel cluster will react with this is a methane molecule. So how if the absorption column filled with this nickel based cluster react with the methane molecule, we have done the screening, and then we have developed the material for the capture of CO2 and the methane. And this is all this is the noodle, it is called noodles diagram, which will give the band gap. Okay, so I think it will be very exhaustive for it. So what is that the major work we are doing? It is intensified steam methane reforming process for high purity hydrogen production with inherent CO2 capture. Whatever you have heard of hydrogen electronic vehicles, right? Electric vehicles and hydrogen based, hydrogen as a fuel. So how hydrogen is produced? From the natural gas. Like they dig the oil from the ground and they refine it, and major portion of the oil will have a methane. If you convert methane to hydrogen, you get the hydrogen. In that process, lot of carbon dioxide is released. So we have developed a method where we can have a hydrogen but without carbon dioxide. In that way, our process got a high uh, good appreciation. So this is all the data which we have used for the AIML application. And as I said, we will not go to the industry to test how our material will work like. So we have a kind of a miniature model in our lab itself, where we will, this is called a reactor, where we fill this reactor with our, this is absorption column. Okay. We we fill this absorption column with our material. This is the material which we have developed. Okay. These are different kind of materials, and we fill this column with this material, and the gas is passed through it. And after this gas is passed through it, how pure is the exhaust gas? Taking the poisonous gases or not, we need to check. So this is the practical way of experimental validation of our computationally designed materials. So there lies the our material is very much um, uh, is in have a very good performance compared to already developed reported material. Okay. Before I finish, I'll just give very briefly about the data. Okay. Data is very important, whether it is for biology, chemistry, they fast over the material design. We have collected the data from the already reported databases, and then fine tuned it, and then tried to understand what are the major parameters. So this, if you compare, if you talk about the data, so these are the research outcomes which we have published in recent times, and also we have patented our method, uh, how it can selectively take away the poisonous gases from the industrial exhaust gases. And these are the papers which we have.
And it's at the comfort level.
With that, I think I have done the first session. I think I can take some of you your questions if you have any. Uh-huh. Propene.
Mobile company, it was.
It
So,
is used for foam and plastic, right?
yes,
Yeah.
polymer industries. And,
Polymer
so
industry.
many industries. In that, I used lanthanum based catalyst.
Lanthanum?
Lanthanum based catalyst. Lanthanum is a very good material. It can react with CO2 and form lanthanum oxycarbonate. When you heat, again, it converts into lanthanum oxide and carbon dioxide. Can you use for that catalyst for?
Lanthanum is very expensive.
Yes, madam, of course. But
That
it can be recyclable, madam.
Even then, over the some few cycles, it can get leached out.
Yes, madam. So
Yeah.
it have,
What we have done, yours is very valid point. What we have done, we have taken very cheap available metal and we have doped this with a lanthanum kind of element
okay, madam.
so that we get the both the
Geolites, if you replace a proton with lanthanum, also one of the
Yeah.
best application methods. And one more thing, I published one paper of mine in ACS catalysis. In that, I taken heteropoly acid, and in that heteropoly acid, I have exchanged the protons with palladium different metals. But palladium only giving CH activation at room temperatures.
Oh,
Remaining metals fail to give the.
it is well
CH
known that
activation.
only noble metals will.
Yes, madam. Actually,
Be-
copper also will give it some data, but rhodium, ruthenium, so many metals I applied. Why this happened? Then I asked for DFT calculation. Palladium gap is very small. In that gap, CC shifting is there. Means palladium coming together. This coming together is examined by CO chemsorption studies, CO2 chemsorption studies, DFT drift studies. From that I calculated, but I did not do anything. Just I given the data to some my junior. He is well good at DFT calculation. But my intention is I should do the both, because now we are doing some experimental data in our Anurag University for same CC coupling. We have experimental data. Now we want to see the DFT calculation for the experiment.
Yeah, one thing I wanted to alert you is DFT methods handling of transition metals is very critical.
Okay, madam.
Because it will overestimate the energies.
Okay.
So, because it's a heavy metal, right?
Yes.
So you need to be very much caution. You have to be very careful about choosing the method.
Okay.
And I think you should go for a very expensive and accurate method. Ab initio methods are very good.
But now what I am using, it is not a noble metal, just heteropoly acid.
Heteropoly acid, no problem. But if you use any catalyst, any noble metal, then you choosing a correct method is very critical.
Okay.
Yeah.
And one more thing, for extension of this work, I am doing a Diels-Alder reaction. I want to calculate DFT for Diels-Alder also.
A Diels-Alder you can do.
Okay, madam.
No problem.
A single catalyst will work for CC coupling and Diels-Alder.
Okay.
And then
for both the reactions.
Both reactions.
Okay.
I want to do the total calculation.
What you do? You just take the reactants.
Okay.
Optimize it. At the same method you also take the products. Optimize it. And then try to calculate the transition state.
Okay.
That is actually, it takes time. So, and then try to understand how it is working for both the reactions.
Okay.
So you'll get a profile, right?
Yes, ma'am.
So, and also you should take the role of solvent.
I am doing first A reaction without solvent, madam. Second reaction in Diels-Alder, I may use some solvent.
Okay. You should take solvent into.
I will come with experimental data to him.
Yeah.
Then we will
Definitely.
discuss. Thank you, madam.
Madam, thank you, madam. One question is, when we do any molecular dynamic simulation for protein ligand complex, it takes a lot of computational power. Is any other methods we can reduce the computational power and we can get a results?
I said QMMM,
Yeah.
right? It is taking time because it is a bigger system. How many atoms are there?
Means most of the proteins we have more than 500 atoms.
500 atoms. As I said, right? you choose a critical, very important portion of your problem.
Binding site.
Yeah, binding site. Okay, active site.
Yeah, it is.
You use the very good method for that,
Okay.
and the rest of it, you use the approximate method.
Okay.
Then you can considerably reduce the time. That is a very, effective way of reducing the computational time.
Okay. Means we have to do the complex for active site and the drug.
Accurate method for the active site and the approximate method for the rest of the
Rest of-
box.
Okay.
Yeah, that
Okay.
way, that way.
Means is any software is available to do that? To do that?
Actually, there is no software even in Gaussian also, because you are defining a problem. You are making a partition.
Partition. Yes.
So there is no software.
Software.
You can just use in any method,
Okay.
any software.
Okay. Okay.
Okay.
Okay.
In input itself, while giving the input, you have to mention that this portion is for this QM
Okay.
and this portion is for MM. Yeah.
Okay. Thank you.
Any other questions? Madam, actually, one question from my side. Actually, you also said that everyone is looking towards AI. But what is the future? Everyone is caring for that actually. No one is happy with that, to my knowledge, because it may rule everything in the future. What do you think? It is really fortunate or unfortunate?
No, if you suppose when we were kids, there was no television, right?
Yeah.
When television arrived, everyone got scared that it will take away our time, and it's nothing like. Now mobiles have come.
Yeah.
Did it change any of our thing? Because
But, this
over
is-
the time, the technology has to come. Now, why AI is important? Because the data. Because if you go to 18th century, 17th century, where the science has just started, okay. For example, Newton, okay, Lee Chatelier, or Dirac, okay. Though when they have done the experiments, there is no knowledge about their any other methods, right? Over the time, over this century, when you come to 21st century, there is so much of data available, so much, right? So if you want to use the such, so you don't want to know whether a particular reaction works or not. You don't want to set up an experiment. It is waste of chemicals, because it's already done there. It is already reported in the literature. It's already available in the data. So how you to use the data? We cannot see you cannot go into every website and then what is this data and then write down. What is the next data? Write down. You cannot do such kind of data entry, right? So there you need automation. Automation will be possible only if there is artificial intelligence and machine learning. Machine learning tools are there for us. Artificial intelligence and machine learning tools will use this data and it will come up with some model. Okay, if you take such chemicals, you will get this product.
Yeah.
If you change any of this method, you will get it will provide us the answers without doing experiments.
Yeah, no doubt, madam. It is doing excellent job, but employees are scaring, nowadays.
No,
Actually.
over the technology, it's getting improved and all. Even in AI also, you get lot of employment. Time will change. Yeah. There's
Including,
nothing to
robotics
worry.
Teachers also, including robotic teachers also came. In the future, we don't.
Because we are seeing we are seeing the application of AI in each and every aspect of our daily life, right? If you open any of your mobile, just based on your tone recognition, it will give you the answer, right? So it's all based on AI.
Thank you.
Thank you, ma'am. Thank you very much for sharing your immense knowledge with us. Dear all the participants, now we'll have lunch and the 12 to 1 Then will be the lunch break. After the lunch break, we'll meet for the second round of the session. Thank you. 1 o'clock. 1 only. 1 only. No, 2. Second session of the, let's start our second round of the today's session. I would like to invite Dr. Sojanya ma'am. Please continue the session. Thank you, ma'am.
Ah. Okay. Talking and talking and actually, I thought this is a more kind of interactive session. So to give you, to make you to understand how important is the data, rather than giving some whatever work we are doing here. So this is the tools we can use for our computational studies. As we discussed, data mining, um, maybe sir was asking about the AI, whether it will replace the computational methods. It will never replace the computational methods, because artificial intelligence and machine learning, the food for it is data. Unless the data is there, we can't do anything, right? So, and the quality of the data is also important. Suppose I have some data for a Diels order reaction. Okay. What are the reactants? What are the products? For each reaction, there are so many Diels order reaction. If I take X, what will be the Y? And what are the reaction condition? So there are so many experimental reports available. So I collect all the data from the reports. But you will be surprised for us to collect such kind of data for sorry. To just collect the data for our problem, for one of our reaction, we took almost 1 year. Why? Because each journal, for Suman, she might have reported some reaction, some VOC for some solar cell in particular reaction condition, and she might have reported some graphs and all. Another faculty will report some kind of study in different conditions. But to do the AI/ML application, we need to normalize the data. We cannot compare oranges and apples. We should have a normal, because finally it is the model, right? So training of the data is very important. We need to have very accurate and normalized data. Normalized data means what? If Suman has carried out at 1 atmosphere pressure at 40 degrees, I have to collect the data only at that condition, not at different conditions. Okay, because such kind of reactions only take place at that condition. Only the reactant and any other parameter is changing. I'm just giving an example. You should not take it very literally. I'm just trying to emphasize that normalization of data is very important. And many of the authors will not report the entire thing. You need to convert the graphical data into digital data. So for one reaction, it took us 1 year to collect the data. That is data mining. And after data collection, cleaning, processing of the data also is very important to make. For example, in COVID, we made a AI/ML model methods for COVID data. So one hospital will report in centigrade. One hospital has reported as centigrade of temperature, like fever and Celsius. One hospital has given no units. And there are so many differences in the data. So cleaning the data, processing and keeping in a normalized way is a very Herculean task. That is the main foundation because this we train this data to develop a model. If this data is itself is not good, it's not properly trained or properly collected, so your model is wrong. You cannot get the accurate results from this model. So getting data mining and there are so many data mining programs like what we have given here. So here, so you can use all these tools to mine the data, and there is so much of automation to collect the data from PDB databases or materials project databases or inorganic structural databases. So you don't need to type each and everything. You just write the script and you can automatically download all the structures related to what you have asked. So there is so much of automation now available to collect the data. You see, these are the references of the publications from which we have from these references we have collected the chemical composition of each catalyst material. This is all these publications have reported something or other result of these catalyst material, and how they prepare the catalyst is also important. So what is the reactor type, and what are the fuel feed, and what is the temperature? So all these parameters is important to collect the data. So here one more example I want to tell you. Like I was telling in the morning that how we have designed the material, catalyst material, to selectively capture CO2 and methane from the industrial flue gases. Here, without doing experiment, we have chosen some 11 solvents, physical solvents. So here, and then we may developed a model, machine learning model, to predict which solvent will have a very good accurate CO2 absorption. So this is actually experiment based on this model. There is one more group in other country. They have validated the model also. So this is one success story. Okay. So coming to this session, actually this is a continuation of morning session, and there are 4 paradigms, right? There are 4 paradigms of science. First one is when during the Newton period or Dirac or anyone, so they have done some experiments and reported the data. So that is the first paradigm. And the second paradigm is the theory and rationalizing. Theory, like why a ball will go only in the downwards. what is the gravitational force. So the classical dynamics. So all these theories have developed in the second paradigm of science. And based on the data generated from the theory, this is the computational modeling, that is the third paradigm of science. From now, we are in the fifth paradigm of science, that is the data. So I have already given the importance of the data. That is the data-driven. Whatever we do now, it is not just a computer bench scale, bench mode experiments. It is the data-driven approach. So first we collect the data and then see the reports and enumerate the data and then see what are the gaps, and then we design the experiments. So that is the fourth paradigm of science. This is one thing we wanted to do, like how the data is useful in every discipline of science, biology, chemistry, or chemical engineering, or anything. So you first step is to collect the data and then analyze the data. And when you analyze the data, you identify the patterns. Like for example, sorry about it. Yeah, here. So, we after first step of data collection, this is the clean processed data. So here you can find out the patterns. Like a pattern is every data collection has a nickel. So that is one pattern. And every most of 80% of this data has used impregnation method. Impregnation is the if you add anything above one material, it is called impregnation. So most of them have used impregnation method. This is one pattern. Like this, you can from the collected data, you can arrive at different patterns. So you identify the patterns and then do the methods whatever. Here it is a business process method for some other application. Here we are using our own methods to explain the patterns that are obtained, and then do the hypothesis testing, and then design of experiments and do the experiments and then validate. So this is the whole thing, data science, you can explain in a nutshell. Actually, there are 4 V's. There is called four V's are very important in data science. One is volume, and another is velocity. Volume is how big is the data, right? You know, how many structures are there, how many points you get. And velocity is how, suppose I report all my data into one database. Okay. How frequently I will update the data. That is the velocity. How big is the velocity of that particular big data. And veracity is the how variable, how variation of the data is, how much is that. Like if you just confine to only one type of material, the veracity is very low. When you have a very wide range of temperature, wide range of material testing, that is veracity. And the veracity and variability is both more or less same. So to collect the data in a big data collection, these are all the important. What I mentioned earlier, data to collect, clean, understand the pattern recognition, and then apply the machine learning or artificial intelligence tools to derive at some pattern recognition. So here, this kind of data interpretation is there in every discipline, like in Facebook, in all social media. It is visible, right, for us. It is already there. Whatever, if you try to open one app, it will continuously, it will show the same app. That is because it has recognized that you are using that one. So you are actually experiencing the big data analytics every day in our life. So we have actually, yeah, there is one link, actually, I forgot to give, it is MPDS, Molecular Property Diagnostics Tool. That is one website where that is in-house developed database. I think it will be very useful for pharmacy, because in that website, once you give the structure of the molecule, it will automatically do all, not automatically, you need to specify the parameters. You can use the docking, you can use the dynamics, all the modules in the same site. You don't need to search for any other software to do every module. All modules are integrated in one at one site. It is called Molecular Property Diagnostic Suite, MPDS. So these are the computational facilities what we have in our lab, and we have almost 40 to 50 workstations, and about a few desktops we don't use, only for data management, and most of our work goes on servers and workstations, and we have access to supercomputing facilities. Otherwise, we cannot do the dynamic calculation. So this is the team which I want to, that Lingaya who has come earlier, he is different. He is a Nagavarapu Lingaya, right? Thank you. He is, yeah, he is a Nakka Lingaya. He is actually he does experimental synthesis. He is a basically catalyst person. He has established several technologies for conversion of biomass to fuels or many other chemicals. And basically, he is a catalyst person. And Dr. Sumana is a chemical engineer. She does AI/ML modeling. And whatever data I give her, she develops the models and generate the prediction. And Chaudhary sir is our distinguished scientist. He is a kind of a mentor for us, because he is from Hindustan Petroleum Chemical, HPCL. And Dr. Yamuna Rani is also a AI/ML scientist. She is heading our department. And below are all our students who are working for PhD and for project student. So that is all I have. I should thank CSR. DST, we have a mission innovation project from which we have very generously, they have funded us to develop a material for capture of CO2. And SERB and BRNS also we have funding. So if that is all about our work and also the computational method. So if you have any questions, I am free to. So any online person can ask the question, or they can? Okay, okay. So thank you very much for your time, and so you are most welcome.
Thank you, ma'am. Thank you for sharing your knowledge and expertise.
are very useful, but what is that you are looking for? How much data you can collect? And how you can clean the data? Because there will be some differences, right?
Yes, sir. Yes.
So that there lies the
Because I done this 3D QA, sir. From that I extracted from Chemable. Sometimes when I searching the whatever the inputs keywords we are giving, sometimes it's giving another thing also. Cleaning the data is little bit difficult. Retrieving the data is very easy, but cleaning the data is
the most important.
yes,
Because the foundation itself is not good, strong.
yes,
The building will collapse. So
yes.
the AI model that we have developed will get.
It's waste only. Yes, okay. Thank you.
Now, I think there are several outlets. In chemistry, for example.
Madam, one question from audience. Is there any provision to use Linux workstation from QM calculation IICT facilities?
Linux only. We don't use Windows. All our machines are Linux based only. Open source.
Is there any provision to use Linux workstation for QM calculations?
Yeah, it's there. Most of the softwares available, they work either for Windows or Linux, both. But we use only Linux.
What can we use? Is there any online cloud?
Our
Facility.
our department doesn't give access over the.
And there are some so we are giving the structure, simple structure, chemical structure. I am giving the data into the
Lakshman T.
Thank you, ma'am. Thank you for sharing your expertise with us. Now I would like to invite Professor Savita Belwal, ma'am, to felicitate our Dr. Sojanya, ma'am. Thank you, ma'am. Thank you, ma'am.